All right, welcome back. Dr. P here, and in this lecture video, we will take a look at some reactions of amines. Start out by looking at, well, reactions that we've seen so far, but from maybe the other way around. What do I mean by that? Well, let's look at alkylation and acylation. And really, I'll just say for alkylation, see last lecture. Why is that? Well, let me just grab the notes here from last time. These SN2 reactions, these are alkylations of amines. So if I have a primary amine, I can react that with an alkyl halide to make a secondary amine. So we've seen that type of alkylation reaction already. Now what about acylation? Well, we saw that a while ago. If we have, let's say, RC double bond OCl, we have an acid chloride. And if we react that with ammonia, and we use some kind of pyridine solvent, or you can do it with excess or two equivalents of ammonia. Basically, you need something that's going to deprotonate things at the end. You guys probably remember that from the mechanism problem. And we'll get this, of course, plus HCl. So we'll get our primary, our primary amide. Now, if we had an acid chloride and a primary amine, and we do this, we will get RC double bond O N R prime H plus HCl. And then if we had a secondary amine, so R prime 2 NH, and we react this in pyridine, a solvent. Sorry if that's a little sloppy, I'm writing a little fast here. Pyridine, Pyridine, we will end up getting RC double bond O N R prime plus HCl. And this guy is not going to, a tertiary amine won't work because we're not going to have a positive charge on that guy. It's not, not terribly stable. Positive charges on ammonium salts are okay. So, we saw that before, quaternary ammonium salts, but not so much for the amides. All right. So we've seen alkylation and you saw acylation in chapter 21, but this is looking at it more from the point of view of the amine and then adding an acyl group to the amine to make an amide. All right. Now, what other types of interesting reactions do we have? Let's see here. We do have something called the Hofmann Elimination reaction. So maybe I will, no, let's write it on the bottom here. Now we've talked about, okay, in 12A we talked about Hofmann products of doing E2 eliminations. The Hofmann elimination reaction specifically makes a Hofmann product via the following method. So let's say we had, let's see, let's do, and let's do NH2. So if I treat this with excess methyl iodide, I will get N, and I'll get 3 methyl groups on it here. So those are my 3 methyl groups. I'm doing bond line formula just to make it a little less crowded, and that's going to have a positive charge. And then we'll have I minus as the counter ion. Now I can treat this with Ag2O in water, so silver oxide in water, and heat it up. And that will give me now 1-hexene. I will get my Hofmann product. Now, how does this work? Well, let's take a closer look. Okay, let's take a closer look at how this Hofmann elimination reaction works. There are 2 kind of main parts here. The first is making use of the fact that your amine is a nucleophile and methylating it, sticking 3 methyl groups on it so that you have this quaternary ammonium salt. Because if I tried to do an E2 here, well, that just wouldn't work, because NH2 minus would be the leaving group, and that's a lousy leaving group. It's worse than OH minus as a leaving group. However, this guy here will leave as trimethylamine, which is a good leaving group. So what we actually have is the following. We have Ag2O, H2O generates OH minus, which displaces I minus. So essentially, instead of having our I minus complex here, the I minus grabs onto the silver and precipitates. Meanwhile, we end up with OH minus, and the OH minus is actually in position to go ahead and do a Hofmann elimination here. So if I go ahead and put in some H's here, and then I've got my N positive charge there, my OH minus here can come along and, oops, sorry about that. I will get my my 1, 2, 3, 4, 5, 6, yeah, my 1-hexene here. Now the question is, well, why do we get that and not the Zaitsev? Well, in this case, the Hofmann product is favored due to bulk of, let's call it steric bulk of leaving group. So in 12A, we saw how a Hofmann product forms when we have a bulky base. So if we use T-butoxide, that can help generate the Hofmann product instead of the Zaitsev product. Well, here we have a bulky leaving group. So it'll look something like this, where, you know, here's our 1, 2, 3, 4, 5. This is actually 1-methylbutyl. Well, this is the intermediate here, the trimethyl ammonium salt here. And you can see, maybe I need to zoom in just a little bit. Hold on here. You can see how, because of the bulk of this leaving group here, we're only going to get certain conformations. And the preferable conformation, which gives us a hydrogen that is anti-coplanar to the leaving group, that preferred conformation will have some steric interference between the leaving group and actually the rest of the molecule. Whereas these hydrogens over here, it's a lot easier to adopt a conformation with a anti-coplanar hydrogen. So they're basically more accessible, and it's actually because of the bulk of the leaving group, not the base. So anyway, I thought that was kind of interesting that it's because of the leaving group and not the base. That explains our Hofmann elimination here. All right. So let's see. What else? Okay. Let's see. I'm just debating if I want to get into this. Yeah, let's start getting into it, and then in the next video I'll wrap things up. But let's look at reactions of aromatic amines. So we'll say anilines. Okay. So, for example, I could take something like aniline and do a regular electrophilic aromatic substitution. So we could do 3Br2 just in water. This is so activated that I'll actually polybrominate this. And we'll get our product here. So EAS NH2 is strongly activating and ortho-para directing. Now, what if we, let's say, let me try to think of some other interesting examples here. What if we wanted to try to do a Friedel-Crafts? Okay, so let's try to do, maybe I'll get another piece of paper for this. Hold on. Now, previously we've seen that I said it was okay to do a Friedel-Crafts on an aniline. But I'm going to ask the question, is that really okay? Because I know we talked about it, but remember, if we try to do a, let's say, a nitration or a sulfonation, oops, sorry, HNO3, H2SO4, we'll get NH4 plus NO2, and this is very slow. Because the acid protonates our amine here. Remember, aniline is a base, so it will get protonated by an acid. And I did kind of harp on this a little bit back in chapter 16. In fact, I think I had you do this, draw the mechanism for this reaction and explain why you got this instead of an ortho-para. Now, we don't see any acid here, however, we do have a Lewis acid. So no Bronsted acid, but we do have a Lewis acid. The problem here is that the nitrogen is still a good nucleophile, a decent nucleophile, and it could complex with the Lewis acid and be then a deactivating group. The other thing is, as this reaction proceeds, we're going to make HCl, which then is an acid and could then protonate our nitrogen there. So maybe not. Okay, but let's make it good. How are we going to make it good? Well, let's take aniline. And let's go ahead and treat this with, we can do acetyl chloride. You could do actually acetic anhydride. That works as well. We'll do pyridine. I think the anhydride will be less likely to do some side reactions. But anyway, the whole point here is that you'll get NH, and we've now made an amide. Now this is still activated. So now I can go ahead and do my Friedel-Crafts. I don't have to worry about this nitrogen forming a complex with this Lewis acid because this nitrogen is not nucleophilic. It's not a Lewis base. So now this will give us that, and now I can go ahead and hydrolyze in NaOH and H2O, and I will regenerate my NH2. I'll still have that guy there, and then I'll have acetic acid that comes off with the OH as acetic acid. But anyway, so in a way this is kind of a protecting group. You can protect amines by turning them into amides. Maybe I'll write that down. Why not? Can protect amines by converting to amides. All right. Okay, so let's see here. Yeah, I think maybe I'll leave it at that for this lecture. And in the next lecture, we'll take a look at heterocyclic amines. And I know we talked about those way back in the first lecture, but I do want to take a closer look at them and some of their unique characteristics. Actually, we looked at them in the second lecture too, didn't we? Looking at basicity of things like pyrrole, or lack of basicity of pyrrole. But we'll look at how maybe some of how they react in the next lecture video. All right, well, until then, stay safe out there. Bye now.